很高兴见到你们这些老朋友。现在因为这个 pandemic， 所以也不能够面对面，但是呢，说的 Zoom 呢也差不多等于面对面，而且好像这个讲话更方便，对不对？你同时可以跟很多人一起同时讲话。所以我呢，第一个要讲的东西是讲这个 probing the nuclear symmetry energy with Rare Isotope Beams， 我从低能慢慢往高能走。所以我要讲的东西，我开始用中文讲，但一下我就转成英文，因为很多名词我不知道怎么用中文怎么讲。So I give an introduction, then 讨论 nuclear equatorial state, nuclear symmetry energy, empirical constraints on symmetry energy, observable sensitive symmetry energy， 最后再 emphasize Pion ratio 跟 symmetry energy， 还有 summary。那 before 我讲的话，我先要 emphasize 一下，我以前并没有对 symmetry 那么有兴趣，但当年李保安在90年代跟我这边待了5、6年的时候，他对 Symmetry 很有兴趣，所以就把我往这边拉进去。所以我们写了一些东西。然后后来陈立文在2002年的时候到我那边去，然后因为陈立文当年也是对 Symmetry 那就很有兴趣，所以我又被他们继续往下带。所以在李保安跟陈立文的影响之下，我开始对 Symmetry 也有一点兴趣了，所以刚开始都是跟他们合写的。然后后来当然徐俊来我这边之后，我们也做了一些关于 Symmetry 的这些东西。后来张震到我这边来的时候，我们就继续做 Symmetry 的机。现在虽然张震已经回去了，但是我们还在 collaborate on some of the study, as I will show later on. So before I start, I'd like to, let me see.Give the chronology of heavy ion collisions. So this is for the young people, especially for young students, to give you the history of heavy ion collisions. So in the 70s, when I was a postdoc, that time we have a heavy ion collision of the energy near Coulomb barrier. So that's one study deep inelastic collisions to discuss how the kinetic energy converts into the internal excitation of the two nuclei. So it's a damping of collective motions. So that lasts about 10 years. And then in the 80s, then we have the heavy ion collisions at the Beverlek at a much higher energy. That's about 1 or 2 GeV per nucleon with a fixed target. And that allows to study nuclear equilibrium states at high density, approximately 3 times normal density. And that's the time I just left Berkeley as a postdoc, then joined Texas A&M University. Now in the 90s, the emphasis going to AGS, going GSI and AGS, and also SPS, go to very much high energy to 10 to 100 GeV per nucleon arcane fixed target. And then the maximum density achieved during that collision can even up to 5 times normal density. We don't believe nucleon can exist at the 5 times normal density. So in heavy ion collision at those energies, quark gluon plus must have been formed. And that the 90s, that's the one the time Bao and Li was with me. Then after 10 years, then we moved to RIC. So that's ultra-relativist energy at the RIC. And of course, RIC energy is very high, so the produce quark gluon process baryon free instead of the baryon rich like AGS. And here this time, I think Li-Wen Chen joined me. But we work a little bit. Yeah, that time we were on both the symmetry energy in medium energy heavy ion collision, also ultra-relativist heavy ion collision at the RIC. Actually, I think Li-Wen Chen did many interesting things related to heavy ion collision at RIC energy at that time. Sorry, what happened? No. So then 2010, of course, LHC started. So you get another increase about more than 10 times in the collision energy. So can reach quark gluon with even higher temperatures. But for this decade to 2020s, of course, we still have RIC going on. LHC continue to do experiments. But now we're talking about beam energy scan and the RIG, also talking future FAIR and the LICA, which is back down to lower energies in order to study baryon-rich coagulon plasma. Essentially, we'll go back to the AGS physics, right? Of course, at the same time, we also have a medium energy machine, for example, at the FRIB at Michigan State, also Rayon in Korea, and also CSR in China. The energy about 250 MeV per nucleon at the fixed targets. Here we can study nuclear symmetry energy up to 2 times normal density. So we'll go back to somewhere early times. Right. So we'll make a circle, start on low energy, go to high energy, then back to low energies. Right. Now let's see what we have learned from, I cannot move my. So let's try to see what we can know about the equilibrium state of symmetric nuclear matter from heavy-ion collisions. I like this slide from Lee and Machalite and Bach. Ko Cheming was in the 90s, so we were together. When he was working with, it was surprising. Lee spent here with Machalite, and he wrote first with Machalite in the, right. So this is the equilibrium state of matters from densities on potential ABs, different parameters, and the tensor interactions, and percentage of neutrons. They are essentially the same here. So the skirm, right. So you can also bilateral given by this one. This is, I think, bound potential. You get this one, and that's the bound potentials. But anyway, the point is, we know a lot about the property of nuclear matter normal densities, but very little at the high density. You see all the predictions are different from each other. Therefore, at that time, the main interest was to find out what the equilibrium state of symmetric nuclear matter. One famous paper is by Pavel Danielewicz, Roy Lacey, and Bill Lynch, published in Science in year 2002. They look at all the flow data at that time, directed flow, dp, dy, elite flow, V2, right. It's as a function of the energies, the beam energies, and those are the data points. And anyway, we don't have to go to the details. The point is somehow to fit those data with transport model, one can determine whether the K0, that's the incompressibility of symmetric nuclear matter. So the data is consistent with K0 between 200 and 300 MeV. Right. But at the same time, and a little bit earlier, right, the Horst Stucker and Barbara Yazak, they wrote a very nice paper in Review Letters in 1984. They tried to use the Pion production and the flow, try to determine equilibrium state. Unfortunately, they failed to extract the stiffness symmetry, the nuclear equilibrium state. The reason is the following. Although difference between cascade and BUU with the mean field can be 40%, so that's the cascade. This is the BUU with, I forgot what the stiff or soft equilibrium state. And here's the data. So by including the mean field, including compression energy, give the better, could bring the Pion yield more consistent with the data, but not quite. Unfortunately, the difference between stiff and soft equilibrium state for the Pion yield is only 15%. On the other hand, the experimental uncertainty is about the same 50%. Therefore, they cannot determine from the Pion yield whether the nuclear equilibrium state at high density is stiff or soft. And that comes to my work with your Eichening in 1985 about the same time, because that paper is 84. So at that time, I would think George Birch was the referee for this paper. Then he told me the paper, then he said, they couldn't determine the equational state from pion yield. Then we came up with the idea of kaon productions at a subthreshold energy, so that gives you the results. Suppose we use the BU with a stiff and a soft equational state, so that is the kaon yield from soft equational state. That's the kaon stiff equational state. The effect is more than factor 2. And that's amazing, because in heavy ion collision, we rarely can find the observable which is sensitive to some physics by factor 2, right? And this maximum density reached about 2.5 normal densities. So rarely you can probe high density symmetric pneumatic properties with the kaon productions. Almost 15 years later, then chaos experiments analyzed by Christian-Fuchs by taking the kaon production from gold on gold, divided by kaon production from carbon on carbon. So you remove all the experimental uncertainties. And then here are the data by the blue band from chaos experiment. And then Christian found out if it's a stiff equatorial state, you get this line. But if you're a soft one, you get the blue ones closer to the data. So some of the substrate kaon production indicate the nuclear matter equation at high density is soft. Soft means around 200 MeV for the compressibility. Now, let's turn to the nuclear symmetry energy. And that's a copy from the famous paper by Bao and Li Wen-Chang. I just joined them, so mainly the contribution from Bao and Li Wen, right? So the symmetry is defined from, you write the energy of a nuclear matter density, isospin symmetry. When isospin is 0, that's the normal nuclear matter equation state, right? This is the symmetry term, that's the isospin symmetry. And that term, you can expand around normal nuclear density, then you get the slope parameter, K parameter, and the J parameters, right? Then from the mass formula at that time, we found the symmetry at about 30 MeV, and the slope parameter from some theoretical values is quite uncertain, between -50 and 200. That's a super soft, that's a super stiff. And then for the K, this term, the certain even larger at the time theoretically. For this symmetric nuclear matter, of course, we know the K0 pretty well from many observable, like the substrate kaon productions and the directed flow, and also giant monopole resonance. But for this term, the asymmetry term, K-sym, that's a large uncertainty, right? And normally people like to use the early days, they like to parameter symmetry and density by that simple formula, but it's which is very naive. 32 rho over rho naught gamma. So if a gamma is large, it's stiff, gamma is small, it's soft. So at that time, gamma has a value somewhat between 0.7 and 1.1. But that's all for lower density. For high density, we don't know anything about the nuclear symmetry energy. Here's the review article by Bao and Zhang. There are many Zhang. I think this Zhang is from Shandong University, right? Give you all the predicted symmetry energies from your density, then you can see it through various widely at high densities, right? Ranges from super soft to super soft, super stiff, super soft, stiff. So nothing is known at high density, and also low density, there's a lot of uncertainty as well. Of course, already we know one can determine symmetry energy from neutron star properties. And again, I took some paper from Bao and his collaborator. This one from Bao and Andrew Steiner. This one Bao from Zhang again. Now, for neutron star physics, the two equations one solved normally is the Toff equations. So you can, once you know the equation state, how the energy density and pressure density, the relations, then you can find the neutron star mass and the radii. So that is the results from that paper. So those x equal to 2, x equal to 1, x equal to 0, x to minus 2 is very stiff, x minus relatively stiff, x0 is the median, right? Somehow from the one solar mass neutron star mass and the radii, if we believe the radii somehow means symmetry energy should be in that regions between x equal to 0 and x to 1. So not super soft, not super stiff. And also from the neutron star tidal deformability, which is lambda, can be written into K2 is a love number. C is defined by the mass of the neutron star divided by radius. And this love parameters, one can solve Einstein equations to get expressed in terms of C and the YR. YR is obtained from these equations with F and the Q depending on the energy density, pressure density, and the mass density in the neutron star at the surface. Anyway, Bauer and Zhang, they found out from there and other information, you can further determine what is the J, not the K sin, or the J, the third term. When we expand the symmetry energy as a density, then the leading term is the S, the next term is L, the third term is K, and it's J. Right? Give some constraint on those. Unfortunately, it varies a lot depending on what conditions one use. So still not quite well determined about the symmetry energy from neutron star properties. Of course, almost 10 years ago, two famous constraints on nuclear symmetry energy, one from Betty Zheng and her collaborator, the other from Latimer and Steiner, right? And that's the L versus S0. Based on a variety of observable isospin analog states, have young observables, Pickenby dipole resonance, and the mass formula, and neutron skin thickness, the neutron star properties, and so on. The conclusion that time, S0 should be about 32 or 32 MeV, and L should be about between 55 and 70 MeV, so relatively smaller L at that time. Then even up to year 2019, again, the Bao and Li and his collaborator, I think that's the Wen Dehua, that's again the Zhang from Shandong, cross-check, I don't know where he's from. Anyway, many observable from both terrestrial experiments, also neutron star observations. They can constrain what the symmetry and the normal density and what the slope parameter at the normal density. The conclusion is it's about 31.6 MeV for the symmetry and normal density. The slope parameter about 58 or 59 MeV. So all smaller L values, even up to 2019. Right. And those numbers still consistent with the earlier, just a year earlier, analysis by my colleague, Jeremy Hort and Yongwang Lin. Now he left A&M, he's now with the Aachen Schwenk in Darmstadt. They published a paper in review letters by looking at the tidal deformability of neutron stars. Then they do the two-dimensional analysis using many kind of equential states to get these distributions, the likelihoods of the value of L, right? And once we know the lambda, then we know what L value is. So there's a probability count plot for the tidal deformability lambda and isospin simultaneous of L for a neutron star of mass 1.4 solar mass. If Jeremy told me they used almost more than 1 million equation states, right? To change the parameter, calculate, or given L, what is the lambda, so they get that probability distributions. Then from here, they extract as the various stereo should be 34 MeV, L should be 50 MeV. And that's consistent with what Baoan show here, right? Consistent with those two values. And at the same time, they get the neutron skin thickness of that 2A is 0.19 plus 0.003 Fermi. And those three numbers consistent with the recent paper by Essek, Tuse, Landry, and Schwenk in that archive paper based on astrophysical constraint and the chiral effect theory. I think Jeremy Holt also has a lot of input from the chiral effect theory input on those equations they use in analysis. That's not surprising, they get similar constraint. So those three numbers, now the point is to get the neutron skin thickness about that value. That value consistent with the old data people measure for neutron skin thickness left to 8. But we all know now we have the new neutron skin thickness measurement by P-Rex that we'll discuss very soon. But now let me turn down some symmetry energy center observables. Previously, I mentioned, I point out a little bit detail on how to constrain the neutron for neutron star properties. I mentioned all the terrestrial experimental constraints on neutron, on the symmetry energies. Here, I just make them explicit. I think I borrowed this list from Baoan's some old slides, right? At the substrate density, we can look at crust yields, neutron skin thickness, giant resonances, isospin fractionation, isoscaling in nuclear multifragmentations, isospin diffusion, neutron proton differential flow, NP ratio of fast pre-equilibrium nucleons in nuclear reactions, triton helium-3 ratio, neutron proton correlation function, and no relative moment. With the high density, one should look at the charge pion ratio and the kaon doublet ratio, and neutron proton differential transverse flow, and NP ratio of freeze out the nucleon perpendicular reaction plane, and the elite flow of a transfer momentum, high transfer nucleons. So I picked a few those observables and then see what's the status of current experimental observations. Now, first talk the symmetry and of the from the dilute nuclear matter, warm dilute matter from cluster productions, and that is the experiments, famous experiment from Netwitz and his collaborator. I think I don't know whether Yugang is involved or not. Right. So what they measure, they just measure the light cluster productions in low energy heavy-ion collisions for two systems. Then from the famous Avogadro formulas, you can construct a yield ratio from one reaction divided from another reaction related to the neutron proton in those reactions. Then you have those two parameters alpha beta that are defined by this Z1A1 for one reactions, Z2A2 is another one, right? So you can, two reactions, you substitute formula, then you can determine the F symmetry. From F symmetry, you can determine the E symmetry. And those are the experimental data points, either the red one, right? And actually, I don't know what's the open one. They're probably similar thing. Those are both of experimental points, probably. Right. And then those the blue line and those dashed line, those kind of stick lines, they are from quantum statistics. You assume a thermal, warm, dilute nuclear matter, the light nuclear yield due to statistical models. When you put it in, then you can fit the symmetry energy very, very well. If you use a naive symmetry energy, like those assume that even the low density nuclear matter, they are uniform, then those are the symmetry energy. The number are much smaller than the symmetry energy of nuclear matter, taking into considering the clustering of nuclear matter into light nuclei. So large symmetry and low density due to the alpha clustering, mainly alpha clusters. So I think that's a very important conclusions from that experiment. Oh, sorry. Of course, Neutron skin in that 2.8 it's known to be related to the slope parameter of symmetry energies. I think I did a borrow from Bawani, some old slides, right? If you look at the densities from that 2.8 as a function of bar, right? Here you give you the proton and the neutron, right? And then you have the weak charge and electric charge, right? Distributions. And then some times ago, I think Alex Brown here I showed the Neutron skin thin that too is very sensitive to the derivative of the constant nuclear neutron equation states, right? It's almost linear there. Therefore, if you measure the neutron skin thickness, one should be able to determine what the slope parameters. And you can understand from kinematically just because the way the neutron being pushed away from the surface is related to the nuclear symmetry force, change with density for the first, right, due to this term, right? And I think the early analysis based on old data of that 2.8 skin thickness, the L value is much, I think it's consistent with those values. But we all know the most recent experiment of P-REX2, right, on neutron skin thickness, right, which is measure neutrons through the parity violating experiment, right? So it's a very difficult experiment because there's weak interactions, so the error bar is large. So the result is the following, right? So this is the experimental neutron skin thickness measured by P-REX2, 0.29 plus minus 0.7 Fermi, which is much larger than older value about 0.2, almost 50% larger, right? And based on that neutron skin thickness, then read Fatoyev and Horowitz as a Picaluvics. They published a paper in Violetta in this year. They extracted the symmetry energy, the normal density is about 38 energy, which is much larger than we normally believe. Normally it should be around 30 MeV or so. And the slope parameter, they claim it's 109 instead of the 50, normally we believe, right? So that is the tension between their results based on the P-REX data with the J and L extracted from other observables, from neutron star properties, as well from other avian observable, nuclear structure observables. Right? And somehow this conclusion supported by Liu and Chen and his collaborator. I think Chen there's Zheng Zhang. I don't know the other two persons. They are too young for me to know them, right? They did a schematical description of P-REX data. I think they did a more careful analysis by Horowitz and et al. Unfortunately, their paper is still not published, right? They, including all the ground state property of giant multiple resonant finding, constraint on the principle of the symmetry method at the supra-saturation density from flow data, density from the flow data, from heavy-ion collisions, neutron star constraint, tidal deformability constraint, mass radius constraint. They did a much more careful analysis than Horowitz, and they got a similar result. As for J, they are almost identical. L is a little bit smaller, but the overlap, if you add the error bar, the comparable. And somehow this paper is still not published. I don't know why. Maybe anyone can tell us why. Right? Anyway, so we have two analysis of the neutron skin analysis claim the L is large, right? Around 85 or 100. Sorry. Oh, sorry. 85 here, it's 110. And also the Schwenk's paper, I think that's another Schwenk's paper here I mentioned. Right? The Schwenk paper also has not been acceptable publication. I think the reason is this L value, the reason is L value too small. I think I had a hard time to convince the referee. I don't know why Liu and Chen's paper, right? This number, some consistent with Horowitz, but still differs a little bit. Maybe that's the reason it hasn't got published. Now, that's another way to determine the traditional way to determine the compressibility is by joining multiple resonances. You can expand the compressibility in terms of isospin asymmetry again. Then this term K tau is the Ka sin I mentioned earlier, right? And then by this analysis by Geiger from Notre Dame, he evaluated Ka as a finger asymmetry. Then from this dependence, he extracted the Ka sin minus 550 plus 100. I think that number is consistent with other analysis as well. For example, from the analysis of Scherer and Miller that's at the Texas A&M. You again look at isoskinning of fragment yielding heavy-ion collisions. Look at those. He looked at the many reactions. Then look at the yield ratio again using the Abel-Regos formulas. Now you can extract the symmetry energies. Right from there, her conclusion is the symmetry energy at normal density about 32 MeV. K is since about 453, which is similar to this number within uncertainties. Of course, the slope parameter is still small, 65, a little bit larger than other constraints, but consistent with larger. So again, those heavy-ion observable give smaller L than the neutron skin thickness analysis. Another way to determine the symmetry energies from isospin diffusions, I think that is an old experiment by Betty Zheng, right? They look at these reactions. You have a 102 to 102, 124 to 124, other combinations, right? And you have many combinations. Then you can construct the observable by that combination. You have 1/4 of them, A plus B, A plus 3 of them. 112 and 112, 124 and 124, 112, 120, that's 3 reactions. You construct these quantities. Then if this quantity is 1, right, that means it's transparency. If it's -1, it's transparency. If it's 0, it's complete isospin mixing. In other way, we want to look at what happened if I have this reaction, what happened of the neutron originated. You have 2 systems, one have a neutron, more neutron rich than the other systems. You want to say how the isospin asymmetry mixed during the reactions, right? If it's complete mixing, then you should get a 0 for that observable quantities. If it's 1, there's no mixing at all. Experimental data, somehow it's half. So there's 50% mixing, right? From Betty's experiment. Of course, when that experiment is published, Liu and Chen that time was at the Texas A&M. Immediately he used Baoani's IPUU code, did that analysis. Right? It's exactly the same analysis. Then he found the 1 minus that's observable. So that's a character. Look at this open circle, depending on equinal state, super soft, steep, super stiff. And that's the data. So somehow symmetry energy. Of course, here it's only central to low density, not high density, right? Below normal densities, right? And that's for this reactions, that for that reactions, although there was a different. what's the difference between it? That's a 50 MeV, that's a 50, I think the two the same. Let me see, there must be something, I missed it. Oh, that's the K async. This is L, right? So he tried L equal to 88 MeV. The K async he tried about 15. So that K async about 500. So consistent with the giant monopole resonance analysis, consistent with Sherry analysis, the isoscaling analysis for K async. L value, of course, this L value at that time consistent with the Li Wenqian's new analysis based on he racks 2 experiments. I don't know whether Li Wenqian was biased by this value or not. He claimed L at that time already 80 plus minus 25. Look, Li Wenqian's new analysis. Sorry. Right. 85, 88. They're consistent. All right. I don't know whether the images you remember that or not. So that analysis was based on about an isospin-dependent IPU model. I think that's quite a sophisticated model. And that model was developed by me in collaboration with Stas Gupta and Chalska at McGill universities based on Gauguin interaction, important Gauguin the finite range interactions. Then you want to replace the finite range then by momentum-dependent interaction. So that is those two terms. Right? So those x values shown here, x equal to 1 super soft, x minus 2 super stiff, x minus stiff, 0 is soft. And of course, in the transform model, you need the collision terms. It's going to depend on cross sections. There's a nice calculation at Ko Cheming and Markolite in the 90s. There's a free cross section in free space, and P is larger than N. In the median, the ratio becomes smaller. There's a free space because the median is small. But in IBU code, the immediate cross section is given by the ratio of the reduced mass in the median in the free space square. And I think the argument is assume the transition matrix independent median, but somehow the phase space and the flux depend on the median. Therefore, the square comes from one from the flux, one from the phase space. So that's the schematic way of including the median effect. Not quite complete because we know the matrix element also depends on the median. You have to use the G matrix rather than the T matrix in the free space. But that at least the first step to go to study the in-median cross sections. As I mentioned, for neutron-proton differential flow, one can show it's sensitive to symmetry, and that's a nice paper again by Barney with his collaborators many, many years ago, right? So you look at directly the neutron-proton flow difference, right? So soft one is attractive, and then you get a stiff one, you become larger, larger flow. So it's sensitive to the stiffer symmetry energies. Indeed, the experiment at the GSI a couple of years ago, by that collaboration, async US collaborations, they found this claim that extract the equation of state for symmetry energy at high density. I think it's consistent with between soft and stiff. Will not come down, not super soft. And also, I think Baoani and his classmates, Ren, I forgot his first name, right? Ren Chang something, right? At that time, somehow we collaborated, wrote 2 papers. We wrote 1 paper in figure light, and Baoani wrote another paper. In figure light, see the MP ratio of pre-equilibrium nucleons can probe the nuclear symmetry energy. Again, you have a super stiff and stiff and relatively soft one. And the symmetry for neutron is repulsive, the symmetric potential of protons attractive in neutron-rich matters. Therefore, you enhance the neutron emissions more than the proton emissions. Then you enhance the N over P ratio for emitted nucleons, and they are sensitive to the symmetry energies, right? So that's the softer symmetry energy, that's a stiff symmetry energy. I don't know that it's measured or not, so I didn't have any data to show here. And of course, the same thing, one can talk about the neutrons difficult to measure. So when Liu and Chen was at Texas A&M, then we see how do we overcome that difficult. So instead of working with the neutron versus proton, with deuteron versus helium-3, so he started the yield ratio of a triton divided by helium-3 using the coalescence model. That's the very popular model for light nuclear productions. Then he looked at these reactions at the very low energies, calcium 52 to calcium 48. I don't know whether they are calcium 52 beam or not. That time we did the calculations with calcium 52. And here's the stiff symmetry and the soft energy, right? So soft energy enhanced triton yield compared to the helium-3 yield, right? Not only in time, also in the energy dependence, right? So that's a stiff symmetry and soft symmetry. So presumably we measure T over helium-3 ratio in intermediate and heavy collision, one can determine the stiffness of the symmetry energy in nuclear matter. And that kind of analysis hasn't been done yet. I think Betty Zheng is planning to do that because they do have good measurement of triton helium-3 in the spirit experiment, which is much higher. Presumably they should be able to see how it depends on the symmetry. And if one has the data, one can do transport model simulations to see which symmetry energy can describe her data. So those experiments will be forthcoming in the near future. That time, and Liu and Chen also did a very interesting calculation, look at the nucleon correlation from HBT in no energy heavy collision between nucleon proton, neutron, proton. Again, he got the conclusions. Once you have a stiff symmetry energy, then neutron will be emitted earlier than the protons. So that will affect like a neutron correlation, proton, and neutron correlations. So that shows the sensitivity of the correlation function depending on stiff and soft symmetry energy. And that, I think, some experiments were done by one of Sherry Shenano's students a couple of years ago, and the result was inconclusive. That, as far as I know, she couldn't draw any conclusions. Right? So I think more experiment effort needs to be devoted to this study if possible. Of course, now come back to the famous Pion yield to Pion ratio. That's a probe of nuclear symmetry at high density. So that's a famous paper by Barney, probably after he left A&M to Arkansas State University, right? So he looked again, those four symmetry energies, super stiff, super soft, the stiff, and the soft. Then he looked at the pi minus, pi plus ratio as the function of stiffness of the symmetry energy. You see the pi plus is almost insensitive to the stiffness symmetry energy. Pi minus increases, therefore pi minus pi ratio increases if the symmetry energy is soft. Now here looks like a big effect, but that's a little misleading. If you look at the numbers, I think that effect only 30%, right? It's 30%. Super stiff to super soft, you enhance the pi minus pi plus ratio by 30%. Remember in the early days by Horst Stucker, And Baba Yazak, they look at the particle to pion yield as how it depends on the normal nuclear matter equational state. It's a 15% effect, right? But that is not the super stiff, not the super soft, just stiff and soft. So if that time, if the Hofstadter using a super stiff symmetric nuclear matter equation, super soft equation state for symmetric, he probably also get a 30%. So if I want to look at this part, stiff and soft, that's probably only 10 or 15%. So again, it's a very tiny effect, but somehow at that time, people did just look at this difference instead of this number. So many people get excited, try to study charge pion production in order to learn of nuclear symmetry and high density. Right? Because at 400 MeV, it can reach a maximum density about 2 or 2.5 normal nuclear matter densities. Right? Indeed, immediately at that time, 4P data, measure pi minus pi power ratio, were available. Immediately, many people did the first calculation. The first one is by Zhigang Xiao and Bao Li and Diwen Chen. They do use IBUU. They found the data can be explained by super soft. But that is confirmed by, I think, by Zhang Fengshou from Beijing Normal University, and his colleague using the Boltzmann-Langevin equations. He also found the data can be explained by super soft equation state. So they claim super soft. And again, this one by, I think Feng Zhaoqing, I think, right? He used IQMD, and then he found that the data can be explained by a stiff symmetry energy at this point. You have to go to low energy to find the sensitivity. High energy is not sensitive. So lowest data is 400 MeV here, right? It's 400 MeV, right? And we also did the RVU calculation with Tae-Soo Song, and it used based on relativistic mean field model. Then we found the equilibrium state between x equal to 0 minus 1. Remember, x0 minus 1 is between stiff and soft, not super soft, not super stiff. So consistent with this one. So now we don't know which one is right. The two calculation claim super soft, two calculation claim it's stiff. Right. Therefore, we start this transform. Sorry, it's a typo. That's MOMD. Transform model evaluation project called TMEP. Right. So we said why we understand why all those transform models give different results. So we invited many transport codes to participate in those kind of studies. So there are many BU type transport codes, many QMD codes. You can, maybe your favorite code is here, like IBU is here, like my RVU is here, like Zheng Zhang's KBU is here. Maybe you also have AMD, you have IQMD, I mean, more than 20 codes. We wrote 5 papers based on that more than 20 codes to study why those transport will give different predictions. So the first study, I think, is led by Zhong Xu, right? He will study heavy ion collision, gold collision at 100 and 408 MeV to compare heavy ion transport code under controlled conditions. In other words, he used Woods-Saxon initial density distribution is a local dense approximation to determine moment distribution, including both mean fields and a constant isotropic cross at 40 millibar. Total, there are 18 codes participated in this comparison study, right? And we look at the transverse moment distribution. You have to look at the directed field, dP, dy. Those are the results from those studies with different codes. The black one are for 100 MeV energy. Red ones are 40 MeV, right? So those are the results from those calculations. So the low energy, they differ by 30%. The high energy, they differ by 13%. They do not agree perfectly. They are of that, or 30%, 13%, right? We didn't study the symmetry energy effect. We just studied the directed flow, right? So already we need to understand why where those differences come from. And they are attributed to differences in the initial distributions, although we have the same initial density distribution, but different momentum distribution, especially in the QMD type. Also, how to treat the collisions, how to include the Pauli blocking in the collision term. Right. Now, we go to the second comparison study. Actually, this is a later study, but somehow it's published this year, that by Maria Canona, that studied the velocity part of the transport model in a box. So we look at symmetric matter of that many nucleons in a cubic box of 20 Fermi on each side with the initial density fluctuations along the z directions. We want to see how that fluctuations propagate in time. So after evolutions, then you have the density distribution as a function of time and space. Then you can take a Fourier transform with the time, with the space. That is the response functions. Fourier transform density distribution with respect to space. That's the response functions. The K, Fourier transform with the space. The omega, Fourier transform with time. So that is the result from all those calculations, right? So they don't agree perfect with each other. Those are the BUU codes, right? They are close, but not quite the same. Those are QMD code, right? Those are two QMD codes. This one's IMQMD, this MQMDL means the lattice formulation of QMD. See, it already tells you there's some intrinsic proper difference between QMD type equation, the velocity equations, and BU type, right? And even among the BUU, they differ a little bit. So we have to understand where the differences come from. Some of different differences, we understand why, were discussed in detail in this paper. It's a long paper, right? And the third publication that's addressed the question that by the first publication, why I understand we get a different flow parameter from different codes. So we'll study collision integral in a box, and that is led by Yinxun Zhang from Institute of Atomic Energy, right? We assume the nucleons of Fermi-Dirac distribution and the secure density and the temperature of two temperatures, either 0 or 5 MeV. But this time 15 codes. I forgot to mention how many codes in this study. I think there are many, many codes as well, right? Because I have here only put the BU code, there are also many QMD codes. Okay. So here 15 codes are consistent within 1% without polyblocking. But once including polyblocking, they start different. So that's the successful collision rates from different codes. They differ, right? So that's expected collision rate. So most codes allow too many collisions to happen. They should be blocked. So somehow polyblocking is very difficult to include rigorously, right? But once in a box, you know how many collisions per unit time, right? So this is the theoretical number, but none of the code can reproduce signal number. In general, QMD codes are worse than the BU code, right? In trivial collisions. And since they all varies, therefore the results from direct flow vary within 15 to 30%. So still effort have to be devoted to improve the polyblocking in transport model simulations. Now we want to include Pion, so the next study is including the Pion, a delta in a bug that is led by Akira Ono from Japan. That's published 2 years ago. Again, we consider both symmetric and asymmetric nuclear matter in box at the normal density at less temperatures, when including N delta, and the time evolution of delta numbers, and also the square dependent would look at many of the collision rates. So there's a summary of all the possible results. That's too complicated to explain in detail. I just tell you what's the conclusions. Uncertain among codes become large for time evolution of delta and pi numbers up to including delta and pi. So they do not agree perfectly among each other. The one that the best is the gem here, and also smash. Right? This tells the error bars. Right? So gem is very good, smash is very good, and some codes are bad in there, some good. So anyway, relative deviation from value in ideal Boltzmann gas. Right? So we're talking about Boltzmann gas, so those are the expected value. So there are also problems or differences among the treatments of pion production, delta production in both BUU type and the QMD type codes. And therefore, they'll need to different prediction on pion productions, therefore pi minus, pi plus ratio. Without understanding these differences, better understand the difference, there's no way we can determine equilibrium state or symmetry from charge pion ratio. Now let's look at experimental data on pion production from this reaction. This should be superscript 132, tin 32 on tin 1 that's very neutron rich, and tin 112 and 1 that's less neutron rich at 270 AMeV at impact 4 Fermi. So there's two collaboration, one experimental collaboration with the Spirit, the other is the transport model evaluation project. This is the paper published in Fixed Letter B, right? And so here's the data point, right? And those are the bands are the predictions from transport models using the stiff or soft symmetry energy. So the difference between results from stiff and soft given by the band, the width of the band, right? Like this code, and this code, the TU-QMD, is very insensitive to symmetry energy for this systems, but it's very sensitive to symmetry energy for this system, all right? And if we look at another code, suppose we look at the UR-QMD, right, being by the purple one, UR-QMD is very well for this system, but not very well in that system. The ratio, double ratio, you take this ratio divided by that ratio, none of them work very well, even the tubing in QMD. Also, you can, the Kai-B is from Zhenzhang, right? This one's close to the data, but not quite. And this, the sensitivity to symmetry is larger than the width of the uncertainty of the data. The width of the red band is uncertainty in experiments, right? So although no transfer model can perfectly describe the data, yet the symmetry in some models is larger than experiment, like this one, Kai-BUU, IQMD BNU, this width is larger than the width. Even UR-QMD is slightly larger. Okay, there's a chance to extract symmetry energy from the experiment data if we can manage to bring this point up here, and this point up here, and that point up here. That's the effort being carried out now. Yeah, I missed one figure. After this one, there's another paper published by the Spirit Collaborations, right? Let me just say in words, right? That's published this year in Figure Lab, collected by Spirit Collaborations, using this code, using the Tübingen QMD, not called Tübingen, called the COQMD, that's a Kotma QMD, right? In that code, they try to extract it from charge pion ratio to extract the symmetry energy. They claim the symmetry energy, the S value is about 34, 35 MeV, like from P-REX2 experiment, signal thickness measurement. And the L value is about 90 or 90 something, 98 or 90 something. So it's between the value extracted by Horowitz from P-REX2 and the L value extracted by Liu and Chen from P-REX data. So at least now the SPIRIT experiments based on charge pion ratios using the tubing QMD, they claim the L value is pretty large, right? Whether all the other transport code authors agree with another, that's a different story. But the tubing QMD is a more complete code than the other codes, as I mentioned briefly in the next slides. In the outlook for the transport event project, the local and the global energy conservation do momentum-dependent fields, right? This one are being studied by the collaboration. So all the codes are now including local and global energy conservation. All the codes provide energy conservation except the tubing QMD that conserve both local and global energy. In RVU and the KBU of Zhenzhang, local energy is conserved, global energy is violated, right? So in that respect, tubing and QMD conserve the total energies and the local energy. Also, Coulomb potential on charged particles that has been studied, I think that by Jiongxu, that is studied by Katzmann, right? The Coulomb potential normally in transmodel treated by using the Coulomb force 1 over R. Then you need to put a cutoff. When 2 by 2 close, then the force blows up. You put a cutoff, and that needs a lot of uncertainties. And again, for the short distance, one should solve the Poisson's equations, and that is indeed done in the tubing QMD. So tubing really treat the Coulomb potential very accurately. Also, if one need to include pion potentials, so pion in water transfer treated as free particles, except in tubing QMD, including the pion potential, both S waves and P waves. Also, all the codes neglect the light nuclei productions, except some of QMD code, like AMD code, but in tubing QMD, including the light year production, like at the end of having calculation through some schematic coalescence picture. Also, effective fluctuations, right? And again, QMD code including fluctuation, BU does not include fluctuations. So again, that says tubing QMD has that strength as well. So that's why tubing QMD is a more complete code than many of the other codes. So that's why Betty Zheng decided to use the tubing QMD to do another analysis of the spirit data from pi ratios and try to extract the L values. I should have included in that slide, sorry. I think I have this slide somewhere, I forgot to put it in here. How much time I have? You gone?
Yeah, oh,
okay, let me try to stop, okay? So that's our look. So I just skip those things, right? So let me just say another thing, right? Another thing I'd like to mention is, right, in all those transport models, the mean field put in, the symmetry put in by hand, has nothing to do with the symmetry calculate from many-body theory. And also, all the transmodel, the force, the mean field input and transmodel, more of them, if you use it to calculate the binding energy of nuclei, they do not give the right binding energies. Except this KBU codes developed by Zheng Zhang and myself, based on the Skirm kind of Skirm interactions based on many nuclear many-body theory interactions. And that's mean fields. We produce all the binding energy of this double matching nuclei. Also get the correct dipole polarizabilities. then he can use it as an input for the transfer model. And that I think is very nice because this KBU somehow can, as a tool you can use to verify the predictions from many-body theory against experimental observations. As I mentioned, in most other transfer models, the mean field put in or the equation put in, right? It's very ad hoc, right? That you cannot find the normal nuclear finite nuclei. So to determine symmetry at a high density from compressed transfer model, we find the with neutron rich, right? So that is the future, the project. Eventually, we hope all the codes applied to the spectral data from charge pion ratio can give the same S and L value. That's our goal. So let's skip all the rest. Then we go to the final conclusion. I just mentioned the pion potential effect, right? The pion potential effect, say the two effects, the Coulomb potential, the pion potential is important. See, the pion potentials, so this one's no pion potentials, right? The charge pion ratio is a function momentum. That's from the Cosmos QMD, right? That's no Coulomb pion potential. Those are with pion potential. They're different. They're affected. Therefore, in order to compare with the experimental measurement, one needs to include the pion potential as well. So let me try to summarize. So I hope I can convince you significant progress we made in dependent symmetry and the subsaturation density with heavy collisions. For example, at a very low density from the cluster abundance, one can determine the symmetry of the extremely substratial energies. Also from reasonably substratial density, you can also determine from isospin diffusion and so on. And unfortunately, the neutron skin thickness of that leads to conflict conclusions, right? I'm not sure, I shouldn't say conclusion. We agree with uncertainty because the Li Chen's analysis and the Harvard analysis, they agree with uncertainties. Although Schwenk's analysis given one, but Schwenk didn't use the P-Rex data, right? He used the neutron star data, same like Jeremy Holt. Nuclear symmetry at the supra-saturation density can be studied from proton-neutron flow difference in charge pion ratios. From proton-neutron flow difference, already they found from GSI, the ASIN US collaboration, they found nuclear symmetry at high density should be stiff, not super stiff, not super stiff. And for charge pion ratio, if we believe in the analysis by Tübingen QMD, then it's also stiff. So different effect, the pion ratio have, but the effect is only 30% between super soft and super stiff one, which is larger than current uncertainty among transfer models. Another I mentioned, the E-median structure effect is to be included in scattering to ensure correct equilibrium pion abundance. That's because the pion delta potential are different. That leads to some threshold effect one has to include in order to be thermodynamically correct. As I've already shown, pion potentials important is to be included. Finally, I emphasize in general based on mean fields and E-median scattering cross-section constraint by pion effect theory, provide the possibility to verify the theoretical predictions on the density-dependent diffusion energy from theory in experiment on nuclear reaction with rare isotopes. So thank you for your attention.
好，谢谢柯老师。所以刚才柯老师做了一个非常精彩的报告，特别是review 了对称能这段时间内的一些进展。那么低密度的对称能呢，现在已经有比较好的确定，但是高密度的对称能现在还是有很大的不确定性。所以呢，这些国际上的一些新的实验的装置，包括美国的弗利伯啊，未来比如像中国的HIAF 啊，还有朝鲜韩国的RON 啊，这些很多的这些装置将来会贡献到高密度对称能的测量。那么包括中子星并合啊、中子皮啊这些，刚才柯老师讲到的这些数据的话，对对称能的 会起到很重要的作用。但是在这里面的话，束应模型是一个非常重要的关键，因为要定量的跟实验数据的结合来提起这个对称能的系数，特别是高密度的这个对称能系数。所以刚才柯老师也讲到了，有一些合作组对吧，发表了几篇联合的文章，来评估这些当代的这些不同版本的束应模型。所以呢，这个领域还是在进一步的发展之中。那么现在大家看看这个柯老师的报告有什么问题跟什么讨论，现在可以提出来。
马老师，我陈立文。
刘文，你讲。
立文你好。
你好，非常精彩的报告啊，就把我们这个过去这个10-20年的这个 community 的一些进展，应该是概括的非常全面，很好。就是你在报告中提到了几个这个关于那个 PREX2 对不对？就是我们
PREX2 OK come here
right
over here no what's PREX2
这很前面的可能是
here
对，就是说这个 paper 我们 submit 到 physical review letters 2个审稿人，就是说也没什么 not too bad OK， 但是他提了一些这个关于这个数据上的这个有一些不确定性的东西，所以我们做了 test。这过去我看大概2-3个月一直在算，因为这个东西我们 essentially 是 fit everything， 我们已经知道了这个。
所以我觉得你们做的 more complete than 这个 Horowitz， 他们只用一个 relativistic mean field model。Right，
他这个是那个 inconsistent with 的这个 neutron star merge 的那些数据，就 gravitational wave 的。所以算这个东西很慢，我们 essentially 已经 finish 了，大概最近可能又 resubmit 吧，可能就是大概是进展是这样的，就是这个工作。对，所以
还有希望在 fixed review letter 发表，对不对？还有希望。
Right， 我是觉得我们还是有一点信心。
Good，
对，所以
因为我觉得，光如果只让他一个不太合理，我觉得这3篇 paper 都应该发表，对不对？
对，
他是这套方法。这个 Schwank 的它是另外一种 approach based on the Neutron， 或者 Schwank 是这个，Schwank 在哪边忘掉了？在哪边？我找不到 Schwank， 这边 Schwank 是 essentially consistent with Jeremy-Holtz， right?
Right.
Based on chiromatic body theory and astrophysical constraints, right? So 这2个其实很相像，对不对？
对，我们和他的可能还是 consistent， 对，有一些 overlap。对，
现在的问题就是说，这个光从 Neutron star 的这个 information 的 L 很小，你从 PREX 的其他的就很大，所以现在2个 group， 所以我不知道 what will happen。
所以它的 Neutron skin 的话也比较小，对不对？实验的如果是比较大的话，它这个可能有点问题，就是它现在这个 Neutron skin 太小了，人家实验大概中心在0.2728了，对不对？29对。
不是，如果你这边你 lower limit 是0.22，跟这个 overlap
a little bit， 对，一点点
，just exact overlap，just touching
right， 所以这可能是原因。还有您刚才说的这个，我们当时那个 isospin-diffusion 的，我们有个88、86，对不对？
对啊，
对，
那个 explain
那个exact 的结果是86。为什么当时我们写的88呢？我们把这个88是根据那个伽马呢，就是你最下面这个参数化
啊，
你会给出来是88，但是如果根据这个 MDI 的 exact 的 interaction 给出来是86，
是86 ，OK，
a little bit different。对，
所以这个 consistent with 你的现在那个fixed review letter paper 这个样。
Right， 所以我们非常 surprise， 就是说这个东西又 go back。
I was surprised， 我说这个 number 跟以前完全一样。
就 starting point 了，又回到这个出发点，又开始回到实际。
不，那时候 density 好像比较 low， 是那时候 density 啊，因为这个是 probe low density， 这个 isospin diffusion 是 probe very low density。
但是我们讨论的是这个 air parameter 嘛，这个就是 around 的这个 normal density。对，我没有其他的，我觉得非常好。谢谢。
好，看看其他人还有什么问题。
柯老师，
这个问题。
谁啊？谁在讲话？
我张一迅。
张一迅，你好，你好。
柯老师你好。
我有 misled 你啊，我讲的你的东西没讲对啊。
没有。我有一个问题啊，就是我看柯老师后面提这个 就是拍不拍正跟流之差去约束这个对称能这个事情。但是我看现在好多文章基本上都是只用其中一个，就是2个同时用的这个，就是他们为啥都不2个同时用过去分析这个？
哪个东西？你再讲一遍什么东西？
就是那个拍不拍正，这不是一个跟实验比的吗？还有这个流的这个之比。
哦，你的 Pion flow， 你的 Pion flow。
对 ，Pion flow， 一个还有那个 Nuclear 那个 flow，V2 那个
Nuclear flow，
就是
Nuclear flow 有啊，那
对
李保安有一个图在这边吗？
就是有没有现在有没有同一个模型？
这个 flow 来的，对不对？
对
flow 来的。
我的问题是
charge pion ratio unfortunately 现在 charge pion 没有办法 ，charge pion ratio 现在没有一个 model 可以 produce charge pion ratio。
哦。
对，
对我当时我的问题就是这个，你看这2个就没有同时，有没有现在有没有同一个 model 去同时分析这2个？
哦 ，I think 谁？那个 Kochman 他可以，因为那个 Betty 的 data 用他的 Pion， 这个他也 involved 在这个 analysis。
哦，
这他 involved 在里面，我相信他 involved 在这个里面 as well。
哦 ，OK，
就是说这个这个什么 ACEOS Kochman also involved， 我相信 ，OK。所以他的 model somehow 因为他很早就开始往这边 move before everybody move in， 所以他的 model comparative 比较 complete， 对不对？我不刚 mention 吗？就是我们没有的东西他都有，这个对，他这些全有，对不对？他 energy conservation 他 yes， 他的 Coulomb potential solve Poisson equation yes， 他有 Pion potential yes， 他 inclinate nuclear yes，
对。
他 include all the， 而且它有 fluctuations， 因为它做 QMD， 对不对？我们做
BU，
我们有 fluctuations。
对，
好。
But of course， 我们都知道 QMD 有个问题，就是 QMD 你的 input equation state 跟你在 code 里面的 equation 不一样。
对，是不一样的。
对，所以 be careful， 就是他会 claim 这是我的 equation state 或者 symmetry energy。但这是 analytic form， 但是在 implement QMD 之后来，其实不是一回事。你最熟的，对不对？那 three bodies term mess things up， 对不对？这是为什么从这边的话，对不对 ？QMD 是 same mean field potentials，same equational state， 对不对？这不同，这就问了，就 QMD treat three body force。
对，还有一点，柯老师，就是除了那个 three body force 那一块。就是 KMD 里边那个，因为它那个就是只有一个包包这么去做嘛，就是它那个 fluctuation 也会带来一部分额外的能量修正，然后让那个状态也变了一点点。
That's right
好，柯老师报告非常好，
柯老师啊，
谁在讲话？
你刚才跟那个列文在讨论那个 P-Rex2 那个 L 的那个测的特别大，然后我就想问
你是谁啊？我问你是谁？啊，我陈建辉啊。
对，我就想问你一下，保安前面有一个把所有的那个数据定出来，那个 L 的参数其实很小的，对不对？
如果你是所以李保安喜欢小的嘛，对不对？李保安最近的 review。
对，我就想问我刚才你跟列文在
他的 L 是他的 L value 嘛？李保安喜欢小的嘛，对不对？李保安不喜欢大的嘛。
对，我就想问这个，你刚才跟列文在讨论说，其实 P-Rex2 那个值是很大，我想问他这个有可能是什么原因？
如果你只看这个 take Neutron skin thickness 这个值非常 serious 0.29， 对不对？那你这个 L 就要很大，因为从这条看过来，对不对？我的 Neutron skin 0.29是在这边，这个是你的 Neutron skin。这边 roughly 是 L， 对不对 ？roughly 是 L， 对不对？所以0.29是在这边很大的，对不对？很大，对。所以当年，所以你在别的方法，所以就用这个，对不对？假设你用如果用这个 Jeremy Holt， 对不对？他的 Neutron skin 只有 0.19， 所以他 L 就小。就是说你的 Neutron skin 越大，你的 L 就越大。
所以主要还是
他在这边，他这边这个有这个 Jeremy Holt， 还有这个 Schwenk， 他们都是 based on chiral many body theory， 他们只是 fit chiral， 然后呢 constrained by the chiral many-body theory 跟 astrophysical constraints， 他得到 S 跟 L， 但是他的 neutron skin thickness 很小，他们就 argue， 他们的 argue 说，哇，这个 skin 这个 P-Rex neutron skin thickness 可能不够准，他说这个不够准，也许将来会变小。现在问题就是 how reliable is this now？
对，它就是总体比较厚度。
Once 你 believe 0.29就变大了，这就为陈立文就变大，对不对？他也是 fit 那个0.29，所以他就得到。我以为他比较小一点点，对不对？他是86，他不是110。那你陈立文刚刚讲，他因为他是86呢，因为他还有其他的 constraint， 这个 Horowitz 他没有用，对，他们是完全 based on 这个 neutron skin thickness， 还有他们这个 relativistic mean field， 他们 claim 他能解释这个所有的 binding energy， 也能解释这个 neutron star， 他们 claim，OK， 所以现在有3个 number， 就是说110 star 的，然后这个 spirit 呢 pi ratio from 白地增大概是100左右，90几，然后陈立文的86。4个 number， 还有这个 traditional 的是50几 ，OK， 就是李保安那些，还有这个50几，就这样有几个 number， 从110一直到50几，当然所以还没有定论，现在这还完全是个 open questions exactly what is L。现在还有人就说我们不应该讨论 L，the point is Betty 跟 Bill Lynch 他说我们不应该讨论 L。What one should talk 是这个东西 ，How to put it？ 我们再看 Symmetry energy curve。你不要看这个在这个 Symmetry energy 在这边的 slope， 你应该看这个怎么这个可以 ，That's the best one。你不要看这个 Symmetry 这个 slope， 你看这个 Symmetry 怎么 depends on density。也许这边 slope has not do with the density of nothing to do with the value of the here, not with the value here。就是 slope 并不 guarantee 我这边的 value 什么的，也不 guarantee 我下面的 value， 对吧？我只知道在 normal density slope， 并不说表示我这边一定非常 steep 或非常 soft， 或这边非常的 steep 非常 soft， 不晓得。
柯老师，
depend 你怎么样的 parameterize 那个 form， 对不对？
柯老师，我有个 comments， 刚才您说的这个东西啊，陈立文，对，这 neutral skin 呢，其实真正决定 neutral skin 的不是在肉磷处的，而是在大概2/3肉磷处的时候的 slope， 所以你可以看到我们刚才那个 Prex 就是这个 PR sub-B 的 PRA 的那个东西，我们非常强调这一点，这也是张震在13年的时候我们最早提出这个 point。但是人们通常喜欢在这个肉磷处，所以这个有点 misleading， right？
这边有一个 figure， 你们的 point 在这边嘛，张震嘛，在这边嘛，对不对？
对，这个是
这点嘛，
这个是它的大小，对，我说的是 neutral skin 真正决定 neutral skin 的是在2/3肉磷处的 slope，
yeah，that's right。然后你 extract 到 normal density， 对不对？
对，其实刚才您说的这个，现在目前这个 L 的几个取值，我们只是说就是说，其实 Prex2 的话，这个 neutron skin 也不是太大。其实在这个基础上，我们也能够 fit everything。这是我们的当时的一个 point。并不是说，但是那个水那个 Horowitz 他们的话是给出来，就是说这个根本就是说不能描写这个 neutron star 的数据啊等等。他们只是 pick up 这个 Prex2， 所以给出这么大的。
That's right, yeah. 他们 lucky， 他们 paper 出来了，
因为他们是最早的，应该是最早的。
Yeah, that's right.
张松，柯老师，我张松。
张松你好。
您提到那个，你好，柯老师，那个 transport model 里边，现在你在考虑这个 fluctuation。这个是在 initial 的，还是在这个 evolution 过程当中的一些 dynamic
evolution 的时候，就是 fluctuation， 因为你在 QMD 它是 每一个 particle， 它不做这个 average， 它每一个 event 的这个 particle distribution 有 fluctuation。但我们做这个 BUU type 呢，你是 average 的很多 ensemble， 所以你都很 smooth。你有 fluctuations 是 numerical fluctuations， 没有 dynamic fluctuations，right？ 那也许 for some especially for light nuclear production 的 dynamic fluctuation 可能很有 effect， 对不对？所以这个，
这个还是统计的一些。高老师，我是马国亮。
马国亮你好。
我没做过这个对称能。那个听了你这个很全面的详细报告，我有个问题就是，我们这个在 transport model 里面 how to introduce 这个 central energy related EOS into transport model？ 咱们是像高能的话是像流体那样的，还是像
好了，给你讲吧。你在用 MPT 对不对？我这边给你看。
啊。
等等，给我找到了，你把那张 figure， 这是你在 AMPT 里面，你开始有这个 Platonic phase， 还有 Hadronic phase， 对不对 ？Platonic phase 呢，也是这个 equation， 但是呢，你把这个 mean field 这项丢掉 ，OK， 这是 mean field，the force， the gradient of potential， 把这个丢掉。在那 Hadronic phase AMPT 呢，有这个 mean field， 但是你在用的时候，你把它 turn off 掉。就在 AMPT 的那个 ART 里面 ，ART 里面有 nuclear 的 mean field， 你把它 turn off 掉，其实有的 ，right？ 所以你用 ART， 比如像张英迅他用 URQMD， 不是就 UR 张英迅，是那个谁用 URQMD 在湖州的那个谁？
金峰、王永嘉。
金峰对不对？他用 URQMD， 王永嘉他们对不对？他们用 URQMD， 对不对？那里面就我找不到那个 figure 哪去了？我再回来这边，这个对不对？在 URQMD 里面，它是 Hadronic evolution， 它原来没有 mean field， 是那个陈金峰跟那个叫他把 mean field 摆进去，对，所以 URQMD 也 participate 在这个 comparison study， 对不对？所以 article 就是你在这个 AMPT 那个 art， 所以 Hadronic 是当年李保安写的，它里面也有 mean field， 但是在我们摆到 AMPT 的时候呢，我们把那个 mean field 又 turned off 掉的 ，OK。在后来徐静在 study 这个 V2 splitting 的时候呢，要 study 那个什么那个你是 study chiral-magnetic wave effect 的时候呢，他又把这 mean field 摆回去了，他就发现这个 protons are repulsive mean field， antiprotons attract mean field。会 lead to the V2 splitting between proton and antiproton. Similarly for K plus and K minus, K plus repulsive potential, K minus 有 attractive potential, it leads to V2 splitting. For Pion 呢也有 mean field 在里边，对不对？所以 in principle art 里面呢，你可以 turn on， 所以如果你要 study 这个你可以把 art 改一改，对不对？如果你要用，你把那个 MP art 拿来，就可以 study 这个 symmetry energy effect。In medium energy hadron collision， 对不对？你 skip 前面的 high，skip 前面的那个 ZPC， 就直接用 art 就行。OK？
好的，明白。谢谢康老师。
懂了吗？
是通过这个 mean field 的这个。
mean field，
好，谢谢。
好，网上老师同学们还有什么问题吗？